So far we discussed instabilities in two systems, Rayleigh-Bénard and rotating convection. Okay. And the first system was 2D and second system was 3D. Now today I am going to work with another system which is like rotating convection, but is magnetoconvection. So we will put magnetic field and temperature. So the idea is, so we have this fluid contained between two plates like this, and I apply a mean magnetic field B naught is along z direction. Okay, so I will assume along z direction, this is along z direction, and of course gravity is downward like this, and there is a fluid in between. Now of course there will be magnetic fluctuations. So we will do that bit later in MHD. So fluid can generate magnetic field, local magnetic fields, like Earth's magnetic field is generated by fluid motion. Okay. So there is a small b which is fluctuation, but I normalized with B naught. So B naught is the magnitude of the mean magnetic field. Okay. So small b is normalized fluctuation. Okay. So this is what is the notation used in literature. So I just followed the literature. So the equation now very similar to what we had before. So let us put all the terms. So you are familiar with these three, right? Pressure gradient, this one also you know, and this one also you know. So what is new? This equation, this term, and this term I will not derive it now, but we will do it bit later when we do MHD. It comes from force J cross B. Okay, so if there is current and there is a magnetic field, so there is a J cross B force. Okay. Now J is like curl of magnetic field under certain approximation. Okay, so this is called MHD approximation.
So what is the small b?
Small b is the fluctuation in magnetic field. So this is fluctuation, and this is well, strictly speaking, B naught times vector B is the fluctuation, and this B naught z cap is the mean magnetic field. So you apply this strong magnetic field with fluid motion, and that fluid motion will generate fluctuations, and that is small B naught times small b. Like Earth magnetic field is dynamic. If you have seen my talk or somewhere, the Earth magnetic field is changing all the time, and you will see that magnetic field here also will change. In fact, we will see consistent equation. Okay. So this is this term we are not, I am not deriving it right now, but you just treat that as a given to you. So we need, of course, how many independent fields we got? We got velocity field, we got magnetic field, and we got temperature. So temperature equation will be same as, okay, so temperature equation I have not written here, is same as before. Okay, so it does not get affected by magnetic field, but we need to write down equation for the magnetic field as well. Okay. So this small fluctuation B naught does not change with time, B naught is constant magnetic field in space and time. We will assume that it does not change with space and time, constant. So the small b is the fluctuation which is evolving by this equation. Again it comes from Maxwell's equation, but we will not derive it right now. Okay. So it has u dot grad B is like advection of the magnetic field, and this term is b dot grad u. Okay. And this magnetic Prandtl number Pm, which I have it here, let us put all of them. Magnetic Prandtl number is nu by eta. Eta is the magnetic diffusivity. Okay. It is just like there is a temperature diffusion. Similarly, magnetic field will diffuse because of conductivity of the material. Electrical conductivity will make it diffuse. No? So that eta is magnetic diffusion. So and this Q is the parameter here, is for Chandrasekhar's number. It is a strength of the J cross B force. You can think of that J cross B force, this J cross B force, no, full the Ampere's force. So, current carrying conductors in a magnetic field experiences a force. So, instead of current carrying conductor, we have current carrying fluid, which is like a wires in some sense, and that is experiencing a force. So, the strength of this term, this non-dimensional number q, which is Chandrasekhar's number, and is given by this, okay, B naught square in CGS units, d squared by 4 pi rho nu eta. Rho is the density of the fluid, eta is kinematic viscosity, eta is the magnetic diffusion. Okay. Now, we will treat that as a number, it is a non-dimensional number. The derivation is simpler for me. Okay, I like CGS. MKS can also be done. In fact, all the engineering books have, or dynamo community also uses MKS SI, but okay, CGS is chosen by some plasma phases, and it is a choice, no problem. If you look at the book, I do also give the formula of SI as well, but right now we just treat as a parameter. Okay. So, these equations are non-dimensionalized right now, it is non-dimensionalized equation. Okay. So, u and b are all, so you see this is non-dimensional. So, u is normalized by kappa by d, b is normalized by b naught, you know, and b naught in turn has basically gone in here. So, b naught does not appear in this equation, you see. Okay. Well, this equation b is also normalized with velocity field. Okay. So, presently just treat them as equations, because this will require some more discussion if I get into that aspect. Okay, so we want to see whether this system is unstable or not. So, in fact, Earth magnetic field is generated by magnetoconvection and rotation. So, you know how the Earth magnetic field is generated. So, let's make some schematic diagram here. So, there are 4 layers. Innermost layer is solid, it is called inner core, and this is called outer core, OC, outer core, and this part is liquid metal, molten iron, chromium and so on. So, this is basically this liquid metal, Lm, liquid metal is around 5000 degrees centigrade temperature, variable, but is of that order, thousands of degrees. So, inner part is hot, there is a radiation there is a heating at the bottom inside, and this part is colder. So, there is a convection in this zone is convection, but it is liquid metal, so it can support current. Unlike water, it can support current, this liquid metal, and that current generates magnetic field. So, Earth's magnetic field is generated here. Okay. And the equations are what I have written here actually. This is, so if we include some rotation in this and make it a bit more complicated, then you have the equation for magnetic field, magnetic generation in the Earth. Now, presently we want to see whether the system will have non-zero u or not. So, instability means we want to see convective motion. So, magnetic field can suppress convection. Well, I mean this I am giving a statement, but this magnetic field can affect convection very strongly. Okay. But we just want to study as a mathematics problem and see whether this will generate convection or not. So, instability analysis, this is an exercise on instability analysis, and so in Fourier space, so I drop the nonlinear term, linear stability, and work in Fourier space. In fact, we will work with Crea-Haring. So, first I write down the velocity field in Fourier space. So, this is Chandrasekhar number, this is that PR square PM magnetic field, and this is convection term, and we have one diffusion term, viscous term. Okay. So, this term is basically new term J cross B term, okay, coming from magnetic field, and this fluctuation B has come, the nonlinear term u dot grad u has been dropped, and B dot grad B, there was a term B dot grad B, that too has been dropped. Now, we need equation for magnetic field. So, if you drop the nonlinear term, we get these 3 terms, this is and this one. This is a diffusion term for the magnetic field. So, these are all positive definite in terms of energy. If I dot this with u dot u star k dot, then this is negative, always negative definite quantity, because if I dot this with u star, what will I get? E of k, and E of k is always positive. U dot u star is always positive, right, as mod square. So, these are all dissipative terms that dissipates energy, but these terms can increase velocity field, right. This is temperature is increasing, this can also do something, okay. This can also increase, decrease. Okay, now we need equation for the temperature, okay, which is same as before. So, now we do Kriya-Haring. So, how many components will we have? So, u will have two components, u1, u2, and b also will have, b is a vector. So, b also will have two components, b1 and b2. Okay. So, there is a k vector. So, there is a, I will use z hat as n hat, and this will be E2 and E1 is here. Okay. So, you can have both E1 U1 U2 for velocity field and V1 V2 for the magnetic field. So, we can derive it, yes.
So, B can have also component among E3 as well?
No. So, del dot B is 0. So, B is also divergence free. So, this is very interesting that U and B both satisfy divergence free condition. Okay. So, now the derivation can be done, but I will not show you here. I will just state the equations. So, this for B1 and this for B2. Okay. Now, it turns out, so these equations, so let us look at the eigenvalues of these. So, the trace is negative, it is of course at least one of them is negative, right. Now, what about the determinant? So, this minus, but minus minus is positive. So, determinant is positive. So, what does it mean about the eigenvalues? Both must be negative. So, determinant is product of lambda 1 lambda 2. So, I know at least one of them is negative. So, that one must also be negative. Okay. So, well, one idea could be that these are complex numbers, but so you can work it out. Okay. So, these are, I can tell you right now that these are negative and they will decay. Negative eigenvalues means it will decay. Now, one interesting point you see, I am not deriving from the first principles. Okay. So, this I did it while I was writing this chapter of the book. So, you can do it yourself, but maybe no need to spend some time on it, save your energy for more difficult tasks. So, u1 b1 and u2 b2 theta are decoupled. So, it turns out because of this structure of the equations, it decouples. So, it is in fact not 5 by 5, there is a 2 by 2 block and 3 by 3 block. So, in some sense, well, if you like, the B1 and U1 component, these components along E1 direction, they are waves, they are not affected by temperature. Okay. Now, these are, you can understand them if you look at the equation more carefully. There is alpha in wave, something called alpha in wave for this MHD, and U1 and B1 are support, these are alpha in waves, U1 and B1, dissipative alpha in waves. So, this I sitting here, that means they are basically oscillations, but they dissipate because of this term.
That's because the temperature gradient is in Z dash.
That is right. So, U2 is affected and B2 is affected by temperature gradient, but not U1 and B1, and this comes nicely from this Kriya-Haring. That is nice thing about it. If you work with Cartesian, it is clumsy, which I have done it, not this problem, but I have done with Cartesian is just is not very transparent. Okay. Now, so we do not need to worry about U1 B1, they will dissipate in a dissipative systems. If Prandtl number was 0 and then this will not dissipate, they support waves. but right now because of this dissipation already present in the system, they will just go to 0. So, u2 b2 theta, this equation may generate instability. Now, that does look complicated. Now, in fact, if you see this part is very similar to this part, right. In fact, these are called Alfvén waves, this I will support Alfvén waves. Okay. And if you look at u2 and theta, so if I drop this q term and b2 term, then we recover the convection equation. So, you can see that they are all consistent, but just in the structure. But since u2 b2 are coupled by this Alfvén coupling, they is a 3 by 3 matrix, not 2 by 2 matrix. Okay, and that will complicate things a bit. So, is that fine? I mean, this is derived from the linear equation. Now, this equation has 3 eigenvalues and 3 eigenvectors. Now, this computer can tell us what are the eigenvalues and eigenvectors, but to see the instability or to look for neutral stability, I just set the determinant to 0, simplest thing to do, because that is where the eigenvalue will cross the 0 line. Okay, from negative to it becomes positive, one eigenvalue, but there is no proof. I mean, this what is by when I do it, I get the same thing what Chandrasekhar gets. Okay, so I am going by faith, I am not really proving it, that all the eigenvalues are negative before, at least the real part, then one of them crosses over, it becomes positive. Is that clear to everyone? So, stable means all the real part, so there could be complex. So, lambda 1, lambda 2, lambda 3, and it has real part, real plus I imaginary. So, real part must be negative for stability. So, real part of all these 3 must be negative if it is stable, but as soon as it crosses 0, so I will say the lambda 2 maybe lambda 3 becomes 0 at some point, and that is what I am curious to see. I have not done it myself, curious to see the eigenvalues. So, this what I want you to, this is another project, that compute the eigenvalues and see when what are the eigenvalues, what is the nature of the eigenvalues. So, I am going to set right now determinant to 0, and the condition we get is this. Now, so we will fix parameters and my variable will be only Rayleigh number. So, I fix Rayleigh, Prandtl number, PM, K, sin zeta is K per by K, right. I mean, that is why. So, Q is also fixed, magnetic field, external magnetic field I fixed, then my Q is fixed. So, I will look for, given these parameters, what is Rayleigh critical, and from here. So, this is of course I can compute Rayleigh critical, no, from here right away. Now, we can do some more. So, this is what it is, Rayleigh critical. Now, we can also compute the eigenvector, and the eigenvector will tell us the structure of the flow. It is a 3D flow, no? Well, it usually is a 2D flow. So, u2, u1 is 0. So, in fact, it is simpler than a rotating convection, and u2 and b2 are related from the eigenvalue. You can eigenvector we can get the relation. So, I will get eigenvector here. So, this is for u2, b2 and theta. So, theta we can choose it to be 1. These are wave modes, no? And please remember, it is sin theta will be sin n pi z and exponential I k x x. Is that in fact it is not a 3D system, it is a 2D system. u2 b2 theta. So, you can take the x z. So, this is u2 is like that. So, I can choose x z plane. So, we can draw this plane and draw the structure. Okay. So, I have not done that work, but we can do it. So, problem would be to find the eigenvalues beyond Rayleigh. So, just go from Rayleigh critical slightly above, see whether they are complex or real or how do you choose. So, this is what I want you to do. An unstable mode, sketch how does U and B look like. Now, here I applied the magnetic field perpendicular to the, well, in the direction of gravity, but you can also apply magnetic field horizontal magnetic field along x axis. X or y are equivalent, no problem. So, you can choose along x axis and you can do the analysis. So, presently, so roll structure is important to see, and so if I do like this, it is easy to see the convection will set the rolls like that, and magnetic field does not want to, it will affect the flow, but it is somewhat happy to let it go like that. You put the magnetic field wants probably flow to go like this, and convection wants to go the flow to like that. So, one has to see, I mean this is a complex structure one needs to understand. Okay. So, this is what I want better understood. So, I just sketched it, but you can see that we need some more work, and one more complex thing could be magnetic field is along some arbitrary direction, then this will affect and this will affect, and the structure will be more complicated. And these liquid metal flows are used by engineers heavily in industry. So, one example which is given is in fact many metals, so titanium, tungsten, or even car sheets. So, you want smooth sheets, so apply strong magnetic field that will smoothen the fluctuations or kill the fluctuations. So, then they want to apply magnetic field and control the convection and things like that. Okay. So, let me summarize what we learned from stability. So, we studied the linearized system. So, these are all part of linear stability analysis. But I did tell you that there are systems that are non-linearly stable. So, non-linearly unstable. So, linear system is always stable. Here we found the linear system is stable for some parameters and becomes unstable for some other parameters, and there is a transition, and that is called neutral stability. Okay. Pipe flow is one example, channel flow, which is stable if you do linear analysis. In fact, dynamo is stable if you do linear analysis, is always remains stable. So, you need nonlinear term to make it unstable. So, we will do dynamo. Okay. So, dynamo is simpler to analyze. Channel flow is one difficulty with channel flow is that I cannot use, well, we can use free slip, but normally the engineering problems we use no slip boundary condition, and then Fourier analysis does not work. So, convection for free slip, Fourier analysis is very good. So, channel flow is what I would like to in fact study this with the free slip boundary condition and see whether we can set it up and what happens. Okay. Employ Cray Herring, it simplifies your calculation, but Cray Herring is not working, does not work for all the time, right. I mean, if you apply no slip, Cray Herring will not work, and that is why channel flow it does not work. But even for those flows, I would like to see what happens with the Cray Herring. So, it does not hurt, no, I mean you just try some new stuff. Look for condition for neutral stability. So, we applied the Cray Herring, then linear, basically we get linear ordinary differential equation for the Fourier modes. So, channel flow, what is the structure? It is like that, right? Now, so this one I would like to put a sine wave. I will treat this as a sine. It is some kind of modeling. So, I want that kind of model, that velocity field. So, instead of really looking for exact profile, but just model with this, and the higher modes will be that. So, just analyze that. So, I do not know if somebody has done it or not, but it is a good thing to try. So, study the eigenvalues and eigenvectors once we get neutral stability, and that will be the structure at the onset, and near the onset, not necessarily at onset, but near the onset structure does not change dramatically if I change the Rayleigh number slightly. Okay, so, it is a good starting point for studying also the later part of Rayleigh. Now, few things which were asked in during the class. So, which modes get excited first? So, the many Fourier modes. So, our analysis tells you that among many modes, one of them is most unstable. So, one with the lowest instability threshold, right. So, how did I get that? So, my parameter was k perp, and I varied k perp and saw that Rayleigh critical was lowest for some particular k perp, and for our problem it was pi by root 2, that kc. Okay. So, we can see among Fourier modes which become unstable, but if I increase my temperature or Rayleigh number, then other modes also get excited. So, other modes also get excited later, but so you can say, well, increased temperature some more modes are getting excited. So, we will get mixture of modes, but nonlinearity also is not going to sit there. So, one example which I would like to say, that if instability means this person has suddenly become rich, getting more and more money, for other people can't simply stop watching that person, say, well, I also want my money. So, nonlinearity will transfer money from one mode to other mode, and that is what nonlinearity does. So, this growth also saturates. So, it's not that people just wait for their turn to come, there is also exchange, and that exchange is by nonlinear coupling, which I will do it after this presentation. So, it kicks in. So, in fact, first we have primary mode, and after that we start putting in nonlinearity, it starts growing in nonlinear. So, first make the primary mode the first mode. So, this one word which is used quite often is called primary mode. So, primary mode wave number, what is the primary mode wave number for Rayleigh Bénard? So, kx is pi by root 2. You just give me the wave number, then I know exactly all of it, all these properties, and ky is or kz is 1, kz is pi, kz is pi, my box size is 1. So, this is my wave number H2D, the ky is 0, and this is a primary mode. Now, when primary mode starts to grow, so we will generate more modes, this is called secondary modes. A secondary mode typically, well, secondary modes can come by instability, as I said here, when I increase the Rayleigh, more modes can come, because other modes also get a chance. But before other modes come, remember Rayleigh critical for n equal to 2 was n4, n equal to 2 takes period of time. If I increase my k, well, so to get a higher harmonics by instability may be taking longer, higher temperature difference, but if I increase temperature a bit, nonlinearity will kick in and it will generate higher modes, which I am going to show you after this. Okay. So, nonlinearity kicks in and it just makes the flow, patterns come, then chaos comes, and this method will not work for no slip, because no slip requires Fourier is not good enough for no slip. Okay, so we will stop here. Thank you.